Good day, everyone. So our topic would still be about acoustics, but this time we are going to discuss about the different behavior of sound. Like the following, we have reflection of sound, interference, refraction, resonance, and Doppler effect. Okay, so we are going to study the definitions of each, and also we are going to look into its applications. Then later on, we will also have some problem solving on Doppler effect. Okay, so let's start. So you can see here, sound waves are produced and then it bounces in a boundary. So that is reflection of sound. An example of reflection of sound is echo. So we have there the incident wave and then the normal line, which is 90 degrees to that boundary. And then you have here the reflected wave. Okay, take note that the angle of incidence is always equal to the angle of reflection. So that is how sound is reflected. So it will also bounce back at a linear path. Okay. Okay, another simple experiment is this one for sound, wherein you have two tubes and then try to orient it so that there will be a same angle, almost same angle from the normal line, and then you check when will you hear the sound loudest, or when will you hear the loudest sound. Okay, as you move the tube, then you check the angle of incidence and the angle of reflection. So that is one possible experiment for reflection of sound. Then you check if the angle of incidence is equal to the angle of reflection. Okay, one example of reflected sound is echo. It's a repetition of the same sound again and again. When do you mostly hear echoes? Okay, in the canyons, in the wells. Then if you also have smooth surfaces. So take note that all those rays will follow the angle of, or the law of reflection, wherein the angle of incidence is equal to the angle of reflection. Now we also have one application of echo, which is the echolocation, wherein the bats are using it, dolphins are also using it, so that they will be able to know the distance of the prey. As you can see here in the illustration, the bat produces sound, and then as it meets an insect, that sound will bounce back, and then they can estimate the distance the sound has traveled and also the actual distance of the bat to the insect, so that they will be able to know how far is their prey. Okay, so again, one application of reflection of sound is echolocation. These are also being used by submarines. So you can do your research on echolocation so that you will be able to find out more applications of echolocation. Okay, let's define it again. Reflection of sound. Sound wave bounces when a boundary is met, and then a reflection of sound is also known as an echo. Now, how much the sound is reflected depends on the material of the boundary. So, for example, let's have this one. So, you can see this is padded wall. So, it's also rough. Is it a good reflector of sound or a good absorber of sound? So for padded walls, wherein it has cushions, so that is actually a good absorber of sound and not a good reflector of sound. Okay, so the sound can die out easily if you have padded walls. That's why padded walls are also used for soundproofing. But to make a livelier sound, you can also use reflectors. We cannot have all padded walls, for example, in theaters. So you can see here an example of reflectors. So you can see in the ceiling, those are reflectors. So it's made up of mirror so that the sound will be reflected and it will become livelier, unlike when you have padded walls. So I want you to look at this illustration, the next illustration. So you have there the stage, and then a sound is produced, let's say by the actress, the actors, and then we have the reflector on top, and then it will bounce back. It will be reflected, or it will be redirected to the audience. Okay. So when we have multiple reflections of sound, that is actually what we call reverberations. Okay? So in sound engineering, they consider reverberation and they consider reflection of sound, depending on the use of the hall. For example, if it's for theaters, musical theaters, they prefer that the sound would be livelier, so they make use of reflectors. But for example, in cinemas, we don't want to have more echoes. Ba, pag nanonood kayo, masyadong maraming echo. So, it will somehow distract us. So, for movie theaters naman, they are using absorbers of sound, like yun nga, padded walls, okay? So, as I have mentioned, reflection of sound, the way sounds are reflected depends on the materials of the boundary. Hard and smooth materials reflect sound better, and rough and soft materials have greater ability to absorb sound. And again, multiple reflections of sound, they are known to be reverberations. Okay, what about refraction of sound? When we say refraction of sound, this time is the changing of the direction of sound because it travels through different media. For example, here in the illustration, you can see here reflection of sound, okay, because we have different temperatures of air. We have different layers of air with different temperatures. So that means they have different densities, so sound will travel at different velocities. That's why it will refract, or it will change its velocity as it travels. Therefore, it will bend. Okay? Refraction of sound is known as, or it involves a change in the direction and speed of waves as they pass from one medium to at the speed of sound. We have velocity equals the velocity at degrees Celsius plus 0.6 times temperature. So the higher the temperature, the faster is the speed of sound. The lower the temperature, the lower is the speed of sound. If we are going to look at this one, okay, so if we are going to look at this illustration, so you can see here the wave fronts are produced. Let's say we have Bucky and Henry, and then Bucky is calling Henry. So as you can see, we have different temperatures. There will be colder temperature at the water surface than the temperature surrounding it, or than the temperature above the water surface. Since there is now difference in temperature, let's take a look at the wave fronts produced. Okay, so you can see here in our animation that we have warmer air and then colder air. At the layer above, there is warmer air, and at the layer below, there's colder air. Okay, so there's the bending of the sound waves. Okay, now another property of sound which I'm going to discuss is about diffraction of sound. Now you can observe na kahit may very, very small opening, let's say sa pintuan, you are not able to lock it or you are not able to close it fully. So merong slit or merong awang or butas. So you can still hear the sound coming from another room or coming from a different room because of diffraction of sound, that it can pass through a slit, but it will bend as it passes through that slit, okay? So that is diffraction. Diffraction of sound is defined as the bending of sound wave through a small opening. So I will show you an animation on that, wherein the smaller the opening or the smaller the slit, the more the sound bends. The wider the slit, hindi masyadong magbe-bend yung sound waves. Diffraction also involves a change in the direction of waves as they pass through an opening or around a barrier in their path, okay? Halimbawa din, let's go back to sa theaters. Pag may mga columns yan, like, ano ba, maraming poste sa theaters, so that could also be a hindrance para sa sound. Because sound waves can actually bend around those columns, okay? Because nga, it can be diffracted also, okay? Next property of sound, which I'm going to discuss, is about interference. Now, you can see here in the animation that you have CR, which is R would be for the rarefaction, then C for the compression. When you have two waves, as they meet, they interfere. They can combine. So the combination, it depends on what is actually being combined. Let's, for example, a compression meets the compression, and then a rarefaction meets the rarefaction. So that will produce a louder sound. But if you have a compression meeting a rarefaction, or a rarefaction meeting a compression, so the amplitude of sound will actually be diminished, so it will produce a softer sound, okay? When it produces louder sound, or yung crest to crest, or trough to trough, or in sound waves we have compression to compression, rarefaction to rarefaction, we call that constructive interference. If you have compression and rarefaction, or crest and trough meeting, we call that destructive interference. Again, constructive interference will produce louder sound, while destructive interference will produce softer sound. Destructive interference could produce softer sound or no sound at all, okay? The next property that we are going to discuss is about the natural frequency of sound. The frequency or frequencies at which object or an object tends to vibrate when hit, struck, plucked, strummed, or somehow disturbed is known as the natural frequency of the object. Get a wine glass. Okay, so we have here a wine glass. If, for example, you struck the wine glass, it has this natural frequency at which it vibrates. That's why it's producing sound. So when you hit it, this will vibrate to its natural frequency and will produce sound, okay? Now, we also have this what we call forced vibration. The tendency of one object to force another adjoining or interconnecting object into vibrational motion is referred to as forced vibration. So forced vibration, I will try to have a demonstration also. For example, you have two wine glasses near each other, and then you are going to place a straw on top of the other one, and then you try to vibrate or set this wine glass into vibration, nandiyan yung straw, and then you will observe what will happen to the straw, okay? So again, we will try this in the laboratory. If we don't have wine glasses, then I'll just take a video of it and then you observe. So that is forced vibration, because one wine glass was set into vibration, the other one was forced to vibrate, okay? So that is forced vibration. Same thing with this illustration wherein you have tuning forks, and then you have here one tuning fork was set to vibrate, therefore it will produce sound, and then the other tuning fork beside it will also produce sound. So that is another example of forced vibration. Okay, recall when you were younger and you are playing in the swing, and then sometimes there's a tendency wherein the swing tends to move higher. Yeah. Parang natsyempohan nyo siya so that it will be at a higher amplitude. Mas mataas na yung swing niya. So that happens if yung frequency ng push, na-meet niya yung natural frequency, or the resonance frequency of the swing. So that is also force vibration or resonance. Okay. Now another demonstration is this. For example, I will produce sounds, and then as I have mentioned, this has natural frequency. So let's have another property of sound, which is resonance. It is a special case of force vibration. The frequency of externally applied force on the body is equal to its natural frequency. So there's a tendency that you will meet the natural frequency of the object. Then the body readily begins to vibrate with increased amplitude. So I'll show you examples of this. One example, yun nga sa swinging. One example is, at a swing, if the push, that frequency meets the natural frequency of the swing, so it will produce a higher amplitude wave. So it will swing at a higher amplitude. So that is resonance. Okay. Another example is this one, Tacoma Narrows Bridge, wherein this bridge has actually collapsed because of resonance. Not the air, the natural frequency of the air, at which the air blows, actually meets the natural frequency of the bridge. And then it started swinging at a higher amplitude, and then it collapsed. Okay? Another example is this one, Angers Bridge disaster, wherein during the collapse, over 4,000 French soldiers were actually marching, because when they march, it's also producing frequency. When that frequency meets the natural frequency of the bridge, then that will produce higher amplitude, and then it might or it can collapse. Okay, so that actually happened with the Angers Bridge disaster. Okay, another example or demonstration of resonance is this. This is natural frequency. We are also producing frequency, and then when we try to produce sound, hindi naman siya na-meet. But there are singers who can actually break glass because of resonance. They produce frequency of sound so that it matches the natural frequency of glass. So this one has is thicker. So I was not able to meet the natural frequency of this one. And hindi rin sa akin tong wine glass na to. So hindi natin siya pwedeng i-break. In the next clip, I'll show you that a person, she's not actually a singer, but she is a physicist. You can follow her YouTube channel. Okay, wherein she demonstrated how she met the natural frequency of this one, and then you check if she can break it.
He brought a wine glass to the space for me to try.
You're really looking to feel the vibration
Yeah,
here.
yeah, down here.
Yeah.
Okay, okay.
And then just reduce the sweeps until you're like, feel like you're right on it. Yeah, we got it. We got it.
It's exhausting.
We got it.
Mike was telling me to try these sweeping noises up to the right pitch. I don't know.
Attempt 3.
Okay, so another example of resonance would be for musical instruments. So you can see here a ukulele. Okay. So of course it has string, and then we have this, what we call the sound box. Okay, ba't kailangan ng sound box? So whenever you tawag doon, strum or pluck, so whenever you strum the guitar string or pluck, yeah, it has a frequency. Okay, it's producing a frequency, and then this one has natural frequency. Then this one has natural frequency. You can see here, you can feel this one. Yeah, you can feel that this is actually vibrating also. So that is also resonance. So that the guitar, the string instruments can actually produce a sound which has higher amplitude. And we have mentioned that if it has a higher amplitude, it will produce a louder sound. Okay. Same with human voice. We also have voice box where the sound that we produce resonates. We also have a sound box where the sound that we produce resonates so that it can be louder. Yan, resonance occurs when two interconnected objects share the same vibrational frequency. When one object is vibrating, it forces the second one to also be in vibration, and then it will result to a larger vibration or will result to a higher amplitude of sound. Now, we also have this experiment. I'm not sure if we can perform this, or I will just look for a demonstration of this one. Wherein, in this experimental setup, you're going to identify the air column at which the sound resonates, or we have to identify the resonating air column, wherein the level of water is actually changed, and then you're going to produce sound using a tuning fork, and then you are going to check when will you produce the loudest sound. Okay, so that one is the resonating air column. Another property of sound is Doppler effect. So what do you observe in the sound that you hear when an ambulance passes by? So when the ambulance approaches you, and then you compare to the sound it produced when it also already recedes from you. Pagpapalayo na siya at saka pagpapalapit. Did you observe any difference? Okay. So if you have observed any difference, what could be the explanation behind it? That's actually physics, which is Doppler effect. Okay, so let's take a look at this animation. If you have a stationary wave, if you have a stationary source of sound, so you can see here the waves formed. And if you're going to compare on the right and on the left, what can you say about the frequency of the sound? Okay, the frequency of the sound, or the number of waves passing through a certain point at a particular period of time, they are the same. Therefore, the pitch of the sound, to the left and right, they are the same. But when the source started to move, you can see here, and you can see on your right side, in the video on your right, you can see there that the waves are actually piling up. So they are compressed. If the waves are compressed, that means that the number of waves passing through at a particular point at a certain period of time increases. If it's compressed, the frequency increases. But you can see on the left side that the frequency decreases because they are farther from one another. Mas farther yung space between the waves. So if frequency of sound on the right side is different from the frequency of sound on the left, therefore we can now say that the pitch of sound is also differs. Iba yung pitch on the right and iba yung pitch on the left. If the ambulance approaches you, so that means the waves in front of the ambulance actually is piling up and the frequency is high. Therefore, you are going to hear a high-pitched sound because of its high-frequency wave. But if it's already moving away from you, you're already at the rear part of the ambulance, so you can see that the waves are no longer compressed. So you have lower frequency. So that is a low-pitched sound. Okay. So now you know why there is a difference in the sound produced by the ambulance if it approaches you and if it recedes from you. Okay. So what is Doppler effect? It is defined as the apparent change in the frequency of sound observed whenever the source of waves is moving with respect to one another or with respect to an observer. This one was discovered by Hans Christian Doppler. There is also a calculation wherein kapag nagkakasalubong yung source and then the receiver or the listener. Higher pitch is heard by the listener at the point where the source is approaching, but lower pitch is heard by the listener at the point where the source recedes. It happens when the source is moving slower than the wave. Okay, this here is an equation describing Doppler effect. We have here the new frequency or the apparent frequency that we hear equals the frequency that the sound is producing over 1 minus the velocity of the source divided by the velocity of sound. Take note also that the velocity of sound is affected by temperature. Another equation, if the source is moving away from the listener, you have apparent frequency f prime equals the frequency actually produced by the source over 1 plus quantity, the velocity of the source, divided by the velocity of sound. Okay. So those are the equations for Doppler effect. Now, another phenomenon which could be associated with Doppler effect are shock waves. Okay. Shock waves happen if we have here an aircraft moving at the speed of sound, or the aircraft is actually moving faster than the speed of sound. So that will be shock waves. They are produced if the source actually moves at the speed of sound or even faster. Okay. Now, if a fast aircraft moves above you, you will hear, if there's a shock wave, you will hear a sonic boom because of the high pressure when the waves are piling up, because of the faster velocity of the source compared to the velocity of the sound. Okay, so those are the different behaviors of sound. We have reflection of sound, refraction, diffraction, interference, and Doppler effect. In the next video, I'll show you some sample problems on Doppler effect. If you have any question, just comment in our group or just comment in the comment section below. So see you in the next lecture. Bye.